You've got goroutines. You've got channels. Now the question is, how do you structure them? Spawning a goroutine per request sounds great until you have 10,000 requests and your server runs out of memory. Processing data step by step sounds fine until each step takes a second and you've got a million records. This episode is about the two patterns that solve these problems: worker pools and pipelines, and how to combine them to build fast, robust concurrent programs. Every goroutine costs memory, around 8 kilobytes for its initial stack, plus the runtime's bookkeeping overhead. If you spawn a goroutine per incoming request, that's fine for 10 requests. For 10,000, you're consuming gigabytes and the garbage collector is fighting your program for CPU. Beyond memory, too many goroutines competing for the same database connection, the same file descriptor, or the same network socket creates contention that slows everything down. The solution is a worker pool, a fixed set of goroutines, say 10 or 20, that all read from a shared job channel. The channel acts as the queue. The goroutines are the workers. You have exactly as many goroutines as you decide is optimal, and no more. The shape is always the same. A jobs channel carries work in, a results channel carries results out, and n goroutines sit in a loop reading from jobs and writing to results. When the sender closes the jobs channel, all workers exit their range loops and finish. Then results gets closed and the collector drains it. The worker function is the simplest part. It takes a receive-only jobs channel and a send-only results channel, and a wait group pointer so the orchestrator can track when it's done. The body is just a range loop. Take a job, process it, send the result. The orchestrator does 4 things in order. First, launch exactly n workers with wait group tracking. Second, send all jobs into the channel and close it. Closing signals all workers to stop after they finish their current job, which is the correct way to tell goroutines no more work coming. Third, in a separate goroutine, wait for all workers to finish, then close the results channel. Fourth, range over results to collect everything. The close ordering is critical. Close jobs first, wait for workers, then close results. If you close results before workers finish, you get a panic when a worker tries to send to a closed channel. The wait group goroutine that closes results ensures this is always done in the right order. Choosing the pool size. For CPU-bound work, runtime.number CPU is a reasonable starting point. You won't benefit from more goroutines than you have cores. For I/O-bound work, network calls, database queries, you can go higher because each goroutine spends most of its time waiting rather than computing. The right number is something you tune with benchmarks. A pipeline is a series of stages connected by channels. Each stage receives values from the previous stage, transforms them, and sends results to the next stage. The key insight is that all stages run concurrently. While stage 2 is processing item 1, stage 1 is already processing item 2. You get overlapping execution without any explicit coordination. The channels do the synchronization. Every pipeline stage follows the same shape. It takes a receive-only input channel, creates an output channel internally, launches a goroutine, and returns the output channel as a receive-only type. The goroutine defers close on the output channel. This is critical. When it ranges over the input and the input closes, the goroutine exits, the defer fires, the output closes, and the next stage's range exits automatically. Close propagates down the pipeline like a domino effect. This shape, a function that takes a channel and returns a channel, is the unit of composition for Go pipelines. You can chain as many stages as you want. You can test each stage independently by just passing it a channel. You can swap stages without touching the rest of the pipeline. Here's a concrete 3-stage pipeline. Generate takes variadic ints, creates an unbuffered channel, launches a goroutine that sends each number and then closes the channel via defer, and returns a receive-only handle to the caller. The goroutine is the stage. Square takes that receive-only channel, creates its own output channel, ranges over the input squaring each number, and returns its output. The channels are the connectors. In main, you just chain the function calls. Generate returns a channel, Square takes it and returns another channel, you range over the final output. When generates goroutine finishes, it closes its output. Squares range exits, its defer fires, its output closes, and mains range exits. No explicit synchronization, the close propagates automatically. Adding a stage is just adding a function call. Removing a stage is just removing one. That's the composability that makes pipelines powerful. Fan-out means reading from one channel with multiple goroutines. Because Go's channel receive is concurrency safe, you can have 10 goroutines all ranging over the same jobs channel, and the runtime distributes jobs. Each job goes to exactly one goroutine. First come, first served. That's fan-out, one source, multiple consumers. This is exactly how a worker pool distributes work. Fan-in is the reverse. Multiple channels merged into one. You need a goroutine per input channel because you can't select over a dynamic number of channels with a compile-time fixed select statement. The fan-in function takes variadic input channels, launches one forwarding goroutine per channel, and uses a wait group to close the output after all inputs are exhausted. The caller sees a single output channel regardless of how many inputs there are. The fan-out/fan-in combination is the basis of parallel processing pipelines. Fan-out work to n workers. Fan-in results from all n workers into one output. You get n-way parallelism with a single clean output to consume. Pipelines need a way to stop. If the consumer exits early because it found what it was looking for or hit an error, the pipeline stages are still running, block trying to send to a channel nobody is reading. That's a goroutine leak. The standard solution is context. You pass a context as the first parameter to every stage. Inside the goroutine, instead of a simple range loop, you use select with two cases, one for normal channel receive and one for CTX. Done. When the context is cancelled, CTX. Done. Fires, the goroutine returns, its output channel closes, and the next stage sees the close and exits too. Cancellation propagates down the pipeline the same way closure does. The same pattern applies to the output send. Use select with the send and CTX. Done, so a stage can exit even if the next stage has stopped receiving. The rules are simple. Pass context first, check CTX. Done in every loop, call defer cancel immediately after creating any context, and use context with timeout when you want a deadline rather than manual cancellation. Use a pipeline when your data changes shape at each step. When stage 1 produces ints, stage 2 produces strings, stage 3 produces structs. Use a worker pool when all jobs have the same type and you want bounded parallelism. 2 pitfalls to avoid. First, goroutine leaks. If you abandon a channel without draining it, the goroutine trying to send blocks forever. Always use context cancellation so every goroutine has a way out even when the consumer stops early. Second, wrong close order. The rule is, close the input channel first, wait for all workers with wait group, then close the output channel. Closing the output before workers finish causes a panic when a worker tries to send to a closed channel. The GoFunc, WG, wait, close, results. Idiom exists precisely to enforce this ordering. A worker pool bounds concurrency. And goroutines share a buffered jobs channel. One wait group tracks completion. Results close after all workers exit. Size the pool for your workload, CPU cores for computation, hire for I/O. A pipeline connects independent transformation stages with channels. Each stage owns its output channel and closes it with defer when done. Close propagates downstream automatically. Fan-out distributes work across n goroutines on one input. Fan-in merges n outputs into one. Context cancellation stops pipelines cleanly. Pass CTX first, select on CTX. Done in every loop, defer cancel immediately. Next episode, the sync package, mutex, RW mutex, wait group, and once for the cases where shared memory is the right tool. This course is based on the complete guide to Go programming. Available on Apple Books and Amazon. Find it at pixelstech.net/book. See you in episode 16.